Our next topic is a little bit different. Instead of evaluating the integral exactly, we're going to talk about how to get a numerical approximation for the value. So this is, of course, for definite integrals only, right? Because you're looking for the area under the curve. But first, I'd like to ask, okay, well, why would we have to do that? Well, it turns out for some integrals, you can't evaluate them exactly. So some integrands have no elementary antiderivative. So this should be, for example, a very famous one, the Gaussian. Let's say I want something like that, right? This comes up in probability all the time. This is actually the bell curve. So if you want to think about like figuring out probabilities and such, you need to do this integral, but this integral is not something that you can do analytically. So people came up with ways to do it numerically, made tables for that. Also, sometimes perhaps you may not need an analytic solution. You might just need the number, figure out the number, and move on with your life, right? So that also happens. Another time where you might need to do this is if you don't actually have a function, but you have, say, a data set. So you want to integrate so perhaps you have information about the rate of something that you measured in a lab and you want to find, say, the net change, right? So you have information about a rate of change and you want to find the net change, but all you have is just the data. You don't know what that function is. So then you could use a numerical approximation to figure out the integral. Okay, so very sort of simple kind of thing. It's just a question of keeping straight what you're doing. So as you know, right, the very standard thing, what is the definite integral? AB f of x dx. So this is the limit as n goes to infinity of this Riemann sum. Right, where delta x was b minus a over n. A and b being the endpoints of the interval. So a very quick and easy thing to find an approximation, well, we're just not going to take a limit, right? We're just going to do this. Now, if you remember what we had on this side originally when we did these Riemann sums, sometimes it was the left endpoint, sometimes it was the right endpoint, but the better choice, the one that gave us the least overshoot from those rectangles, was the midpoint, okay? So these are your rectangles, and so here we have n rectangles. So if I want to write this down, I'm just literally do this, exactly the same thing with n things, n subintervals. But I'm going to say choose the midpoint. So let's write that down. Midpoint rule. And this we've seen before, and I'm going to call it mn. So this is approximately this thing. This is equal to, right? It's equal to this, but this is an approximation for the integral is what I mean. And then for this xi star, then we're going to use the midpoint of the intervals, okay? So let me rewrite that. So what is that midpoint and all this? We've got where delta x is b minus a over n, and then your midpoint is going to be xi minus 1 plus xi over 2. So if you remember how we did this way back when, we would take our interval from a to b and we divide it up into n subintervals, right? And the way they were indexed was the beginning one was x0, the last one was xn, And sort of your arbitrary interval in the middle went from xi minus 1 to xi. So for our midpoint rule, we've divided into n intervals, and then we need to find the midpoint of each of those intervals. That's this xi bar, and then evaluate our function at those points. So, of course, what this is going to look like is just f of x1 bar plus f of x2 bar plus all the way f of xn bar times delta x. Whoops, like that. Right, or we could put the delta x in the front, which probably I will when I write them all, but this is that. So let me do an example of this. But let me first draw up my example kind of nicely. So let me share with you a GeoGebra worksheet, which is linked on our Canvas. This is the function that we're talking about, and I chose from 0 to pi. We didn't really have pi, so I put that in. And n equals 3. So the integral that we are going to be looking at here is this, sine x squared dx. So we're trying to approximate the area under that curve. So this little thing actually is quite nice because you can put in the function, you can put in the endpoints, and then there is, and I've chose n equals 8, okay? So from 0 to pi, I've broken it up into 8 pieces, and then you can see in the middle there that the rectangle goes up to the middle. And of course, it's the same thing as you'd expect, as we've seen before. As I increase the number of rectangles, I get a better picture for what that area looks like, right? Okay, so let's see how we do that. Okay, so first of all, you see actually on the right hand side here, I've clicked midpoint, but we're going to talk about all 3 of these rules because you need to know all 3 of them. So we will come back to this example. So you can just have this picture in your head, but now I'm going to go back to the board and kind of work it out. All right, so I'm going to make a little chart like this for our problem, because then we're going to be using this same example. I'll just put it up here and we can keep it. So this is 0 and pi, and we are going to compute M8 like I had in the picture. So n is going to be 8, right? So delta x is going to be pi minus 0 over 8, so clearly pi over 8. Okay, so in fact, I can just put that here, pi over 8 times. And then f of x is sine of x squared, but I need to know what points to evaluate it at. So first of all, I'm going to take my partition and I'm going to break it up. So I'm going to actually just draw the partition, right? So I'm going to take this and draw it into 8 pieces. So, but that's quite easy, right? And then I'm going to write down what I have here. I got pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. I'm just counting them out, right? And you can keep them with an 8 in the bottom if you want, or I mean, because I put the reduced form, that's fine. Okay, so those are the points that are at the ends of my each interval, all right? But because I'm doing the midpoint rule, I need the midpoint, right? So the midpoints, I can work them out with this formula, but I can also sort of do it mentally, right? Because it's halfway between 0 and pi over 8, so it's pi over 16, right? And then the next one is going to be 3 pi over 16, and blah, 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 till this last one is going to be 15 pi over 16, right? So I just kind of can work that out. And for all 8 of those intervals, I need that middle point because I'm going to be evaluating my function there at that middle point. So the function, again, is sine of x squared is what I'm trying to integrate. So I'm just going to put those points in. Sine of pi over 16 squared. And I just keep going. I put them all in. And blah, 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 all 8. Right, all of that times delta x, and my answer is, oh, I had it here, let me check it out, 0.8175. If you put all those into your calculator. Okay, so that is the midpoint rule with this particular integral.